Next thing we're going to take a look at is how the presence of particles, specifically non-volatile solutes, the effect that they have on the boiling point and also the freezing point of a solution. And what these do, presence of non-volatile solutes, is that they actually raise the boiling point of a solution. So in other words, then the solution boils at a higher temperature than the pure solvent. And there's another side to this coin, in that it lowers the freezing point of that solution. So BP is boiling point, FP is freezing point of a solution as well, compared to the pure solvent, right? And this is one of the two sides of the same coin in terms of raising the boiling point, lowering the freezing point. So compared to the pure solvent. Okay, and we can actually visualize this on a phase diagram. So the phase diagram here in blue, we'll highlight this in blue, represents our typical phase diagram we've seen before. And on this, we can draw a horizontal line at the 1 atmosphere pressure, which represents normal conditions. Okay, so we know that the normal boiling point of a solvent is the temperature at 1 atmosphere at which the liquid turns into the gas phase. So this would be the normal boiling point right about here. And then the normal freezing point, in this case of whatever this is, water, is at 1 atmosphere, the temperature at which it goes from a liquid to a solid. All right, so that's this region here. Now, if we were to plot the same information for a solution rather than a pure solvent, what we would actually see is the graph in orange, where those lines actually are in a different location on our phase diagram. Okay, so for the freezing point is actually now lowered to maybe here. So this would be the freezing point. Again, this is at 1 atmosphere. So the freezing point gets lowered from whatever this is to whatever this is now. And then the opposite is true. The boiling point gets raised or elevated from this point here to a new point. So the boiling point is raised or elevated is another term that we'll see. Okay. So and again, this is for when we have our non-volatile, meaning our solutes that don't vaporize very easily. We see that the boiling point gets elevated for the solution, the freezing point gets lowered for the solution. So the change then in the boiling point, for example, so delta T, change in temperature for the boiling point, is actually proportional to the M, or the molality concentration. Okay, so that means as the molality, as the amount of solid particles increase, that boiling point is actually raised by a greater degree or greater amount. We can replace that proportionality symbol with an equal sign. Then we need to introduce now a proportionality constant, KB, and this is called then the boiling point constant, the boiling point elevation constant for that particular solvent, right? And this is something we can look up in our tables. So we can calculate the change in the boiling point for a solution relative to the pure solvent if we know what this constant is and if we know what the molal concentration for that solution is. Remember, the change in boiling point, change in anything, will be the boiling point for the solution. So the solution boiling point, subtract the boiling point for the pure solvent. Okay, there's a similar relationship that we can see for the freezing point depression. So the the change in the freezing point, or the lowering of the freezing point. Delta T F subscript now would be the freezing point of the pure solvent minus the freezing point of the solution. Okay, and that change, the delta TF, then again proportional to the mole concentration. We make it an equality. We now introduce a freezing point depression constant to incorporate into that equation. So we can calculate what the change in freezing point is going to be if we know what the mole concentration is, and if we know what the freezing point depression constant is, right? That's a constant we can look up in our tables, or we'll be provided with it. So we can rationalize, for example, the depression of the freezing point by comparing the entropies again of the solution compared to the pure solvent. Okay, so if you compare just the starting point, so the entropy of the pure solvent compared to the entropy of the solution, you'll notice that the solution has a higher entropy than the pure solvent. But both of these, in order to freeze, they both need to get to the same endpoint, which is the solid, and the solid has the same entropy in both cases. Now, because there's a bigger difference in entropy here from the solution to the solid, compared to going from the solvent to the pure solvent to the solid. What this means then is that we need to actually remove more energy from the solution to convert it to a solid, then we would need to remove the energy from the solvent to convert it to a solid. So since we need to remove more energy on the right side here, that means then that the solution is going to freeze at a much lower temperature than the solvent would. Okay, and there are direct implications for freezing point depressions, for example. So in the wintertime, for instance, the maintenance crews on the highways, right, they salt the roads. Okay, and what that does is it lowers the freezing point. Or maybe you salt your driveway at home, or where you live, around where you live. And what that does is it lowers the freezing point of water, so that in order for the water to freeze into ice, it needs to actually get a lot colder. So what that means is the water stays as a liquid at a much lower temperature, so it doesn't ice over as quickly. Now, if the temperature gets super cold, then no amount of salt you can add is going to help. But in cases where, you're hovering just under the freezing point, 0 degrees Celsius, that can help in some cases. So here we have some boiling point elevation constants and also freezing point depression constants for several very common substances, water being the most common one, but there are other ones that we see down here as well.